Now, after a star has gone red giant, what is left is a white dwarf. And we're going to back up just for a quick moment. At the end of all of this planetary nebula, there is a very, very dim but hot star down in that center, which is a white dwarf. They're small, they're blue indicating they're quite hot, but these white dwarfs are, I want you to think of a white dwarf as a retired star, okay? If you think of your grandparent who might be retired, if someone is retired, they are usually no longer making money. They are living off what the money that they made in the past. That is exactly what is happening with a white dwarf. A white dwarf is not big enough or hot enough anymore to have nuclear fusion. It is just plain no longer at the point of its life that it can produce new fusion. It doesn't have the pressure or the temperature or the fuel in its core to do this. But it still has a little savings left, and so that's what it's living off of. All stars that are 8 to 10 times the mass of our sun will end up as white dwarfs. Now, bigger stars turn into exotic things, neutron stars and black holes, and we will get to those, but not quite yet. Through planetary nebula, a lot of the mass gets thrown outward, and if the mass that's left after all of the planetary nebula have been ejected are 0.6 to 1.5 times the solar mass, you're going to end up with a white dwarf star. Now, when that white dwarf is produced, whatever is left after all of those nebula, you end up with this tiny little white star. The core is going to be mostly made of carbon, oxygen, nitrogen, things that are very poor fuels. If you remember our little graph here, all that's remaining in the star is really, really bad fuel that doesn't burn terribly well at all. And it doesn't have the mass and it doesn't have the pressure anymore to keep the nuclear furnace going. And so it's going to just use up leftover heat. Leftover heat is what is going to make that star shine. White dwarfs are small, very small, about 60% of the sun's mass, and they're very, very dense. So, for example, if this is a kind of a comparative set of pictures, if this gives you an idea of how big the sun is now, a white dwarf in comparison is going to be about that size. We estimate that our sun, when it goes white dwarf, will just be a smidge larger than planet Earth. So we're talking about something that is really, really dense. The sun itself right now is made of a lot of gases and plasma. There is a lot of heat that keeps the whole thing kind of blown up like a big hot air balloon. When you remove that heat and you have it reduced down to nothing but very dense solids, you get something that is quite dense. The density is insane, crazy dense. To give you kind of an idea, if you had 1 teaspoon full of white dwarf matter, it would weigh approximately 5 tons. Now, I don't know about you, but I can't picture 5 tons. So here's some things to kind of help. Shamu the whale, if you've ever been to a SeaWorld or something like that, if you see a killer whale, these things weigh approximately 5 tons. Roads. If they have weight bands on roads and bridges, they very often have a limit on them, no more than 5 tons per axle. It is a huge amount. 5 tons is about 10,000 pounds, or yeah, that's big. That is just, 1 teaspoon would weigh approximately 4 mid-size cars. So that's another thing to give you an idea of how heavy white dwarf matter would be. The white dwarf, remember, is living off of its retirement funds. And the red giant, as it cools and goes through these planetary nebula and goes into a white dwarf, we're going to end up in this corner of the Hertzsprung-Russell diagram. These things are hot. There's a lot of heat left over, but they're getting dimmer and dimmer and dimmer through time, and they're getting cooler through time. And so the white dwarf, as it uses up its heat, will start off white. As it cools, it's going to turn red. As it cools further, it's going to turn into a brown dwarf, and a black dwarf. There's not necessarily a sharp dividing line between each one of these. It's just the slow process of the bonfire going out. And as that bonfire goes out, we're eventually going to end up with a black dwarf. And a black dwarf is a cinder. It is the lump of coal that is left over after a star has lived a good life. We see these just because some of them that aren't totally dead yet give off a tiny amount of heat in the infrared part of the spectrum, but they are just little cinders of stars that are roaming around the galaxy. We think a main sequence star like our sun, about 10 billion years, birth to death, and that's how it works. Now, we are going to next start talking about the weird, the wacky, and the exotic. So one more time, our star, stellar nebula, average star, burns mostly hydrogen plus hydrogen to create helium. When that fuel gets exhausted, we start using bigger but less efficient fuel. Red giant, as the red giant starts to die, every time it switches fuel, it produces a planetary nebula, and that way it throws gases back out into the universe so that the matter can be recycled to make more stars. And that little retired star in the center is a white dwarf, and that white dwarf will eventually, the fire's going to go out into a black dwarf. Now, what we're going to start into next is some of the weird and crazies, like nova and supernova, and we'll get to the rest in a bit. So we'll see you next time. Bye-bye.